Hello. So this is our final video on the last worksheet, Zeno's paradox. Let's jump right to it. Okay. So let's see what Zeno's paradox is about. The story of Zeno's paradox, there's actually a couple different versions, but the version I want to tell you is about a foot race between Achilles and Tortoise. The tortoise is slower than Achilles. Achilles is, let's say, twice as fast as as Tortoise. But Tortoise starts 100 meters ahead. So let's say they're 100 meters apart when they start. So Achilles is twice as fast. So by the time Achilles catches up to where the tortoise started, which is 100 meters ahead, the tortoise has traveled 50 meters ahead of where the starting point. So in that time, the gap closed to half of the distance. And so Achilles will try to catch up, runs 50 meters more. But by that time, the tortoise has moved 25 meters ahead. And so on, right? So when Achilles reaches 25 meters more, tortoise has moved half of that, so 12.5 meters. And in that time, the tortoise can move 6.25 meters, and so on. This will go on forever, right? So here's Zeno's paradox. Before Achilles could catch up to the tortoise, we have to accomplish all of these steps. By the time Achilles catches up to where the tortoise used to be, tortoise has moved on ahead, so there's more distance Achilles must cover. And it seems like you could repeat this infinitely many times, and there's infinitely many tasks Achilles must accomplish before he catches up to tortoise. It seems like it can never happen. On the other hand, we know that this conclusion is wrong, because if Achilles is running faster than tortoise, of course it's going to catch up eventually. So this breaking it up into infinitely many steps is nonsense. You must catch up at some point. So there's two contradictory points of view, and I want you to decipher it. And in fact, we actually know enough mathematics from the last worksheet to fully answer this question. So I think what I want to call your attention to is geometric series formula. So this is a formula that we covered in the last worksheet. And in particular, we covered it when r was equal to 1/2. So 1 plus 1/2 plus 1/4 plus 1/8 and so on. In this case, the r is 1/2. So each term you're adding in your infinite series is 1/2 of the quantity beforehand. And when you have an addition like this, where each term is some constant times the previous term, we have what's called geometric series. And then we did some algebra to prove that the sum is 1 over 1 minus r, or in this case, 1 over 1 minus 1/2, which simplifies down to 2. So we could do a computation kind of just like this. In fact, if we take this computation right here, we can translate this into Achilles and tortoise situation. So he wasn't running 1 meter and 1/2 meter, but if you multiply both sides of the equation by 100, we get 100 plus 50 plus 25 plus 12.5. So these are 1 times 100, 1/2 times 100, 1/4 times 100, 1/8 times 100, and so on. So if you multiply the left-hand side of the equation by 100, what we get is 100 times the right-hand side as well, right? So 100 divided by 1 minus 1/2, which simplifies down to 100 times 2, or 200 meters. So what is this computation saying? So if you add up 100 meters plus 50 meters plus 25 meters and so on, infinitely many times, it actually doesn't blow up to infinity. It gets closer and closer to 200 meters. So Achilles could accomplish these infinitely many tasks and catches up to tortoise at 200-meter mark, which is what you might expect if you try to do this computation as you might have done in algebra class. So actually, the two different points of view actually leads you to the same answer if you know this geometric series formula. Okay, so I did skip some of the questions here. So you can pause the video now to fill out some of the questions that I've skipped. Then I'll move on to the next bit. So the next bit that I want to talk about is the question of convergence and divergence. So it turns out that the mathematics of adding infinitely many things is a little bit tricky. Sometimes it gives you a sensical answer that makes sense from the situation, like the Zeno's Achilles versus tortoise situation. We gotta answer that made sense. But sometimes we get some nonsense answers, and this was kind of hinted at in the previous worksheet as well, where we had a situation where we had a $1 and negative $1 canceling out in different ways, where you could end up with different amounts of money in the end. You want to only be able to deal with a situation where the formula is actually giving you sensical answers. So you have to look at these things carefully. So convergence means, yes, the infinite addition is getting closer and closer to a particular number, and it makes sense. And divergent is a case where the addition is not getting closer to a number. So you shouldn't expect there to be a concrete answer in the end. So it turns out that in the case of geometric series, the answer we get only makes sense when these R is strictly between +1 and -1. If you're adding number, if you're adding like R to the nth power, and R is between -1 and 1, it's getting smaller and smaller as you take higher and higher powers of it. So it kind of makes sense that these are the situation where it does converge. It turns out that just because the things that you're adding are getting smaller doesn't necessarily mean it's convergent in general. But in this case, for the case of geometric series, yes, that is the answer. So as long as you're plugging in R strictly between -1 and 1, it gives you an answer that makes sense. You should try to plug in the formula with R equals to 2 and convince yourself that left-hand side and right-hand side cannot possibly be equal. Okay. So There's a interesting consequence we can get from this geometric series formula and situations where you have repeating decimal digits. So it turns out that you could use geometric series to show that 0.9999999 repeating is same thing as exactly 1. And you could prove it using the geometric series formula that we have above. Okay, so the left-hand side, 0.99999 could be written as 9/10 plus 9 over 100 plus 9 over 1000 plus 9 over 10,000 and so on. This is 0.9, 0.09, 0.009, and so on. If you look at this and factor out 9 over 10 from each of the terms, you could rewrite the sum in this way. Okay, the first term is 1 times 9/10. The next term is 9 over 100 here. This is the same thing as 9/10 times 1 over 10th. So you're multiplying each term by a factor of 1/10. Right? And you can kind of see that inside this parentheses, we have a geometric series. So we have 9/10 times 1 over 1 minus the factor in this sum is 1/10. Okay, this is 9/10 times 1 over 9/10. Right, 1 minus 1/10 is 9/10. And if you take 9/10 and divide by 9/10, we get 1. So it turns out that this 0.999999 is exactly equal to 1. You could do tricky things with a repeating decimal digit that involves more than one digit. You could rewrite this decimal 2.3232. So it's 2323 repeating. You could look at the first two digits. That's 2.3, same thing as 23 over 10. The next term, 0.023, is same thing as 23 over 1000. And 23 over, what is that, 100,000? And so on. You could rewrite it as 23 over 10 times 1 plus 1/100th plus 1 over 100th squared, and so on. So I think I'm not going to finish the computation here, but you could see that this is the same thing as geometric series. So you could rewrite this as a fraction. And you can work out what 2.3232, like this repeating decimal thing. If you want to rewrite it as a fraction, you can find a fraction using this method. Okay, so I hope you found that interesting. There's usually on a calculator, there's a button that makes decimal into fractions and fraction into decimal, and decimal into fraction is a very useful button. But I used to wonder how calculators are doing those things. But now you have a method to compute it yourself as well. So if you use geometric series, every repeating decimals could be rewritten as a fraction. And this is exactly the method you could use. Pretty cool, right? One more small thing. So this is more of a brain teaser. So let's say we have A equals to B. So we start with this situation. It could be any number, like A and B could maybe both be equal to 7 or whatever. If you add, using the rules of algebra, if you add B to both sides of the equation, here's what we get. And then we could subtract 2A from both sides of the equation. We get this situation. And on the left-hand side of this equation, we have A and negative 2A. So you can collect like terms and reduce it to B minus A. On the right-hand side, both of the terms 2B and 2A has 2 in it. So you could factor out the 2 and get 2 times B minus A. And finally, if you get to this step and divide both sides by B minus A, you can cancel that out and get 1 is equal to 2. So 1 equals to 2 is obviously not true. So we actually did something wrong here. And the question is whether you can figure out where the mistake is. And try to see where did we break some rule of algebra. I encourage you to pause and try it out. And if you can't figure out where things went wrong, replace letters with concrete numbers so it's easier to follow. Like plug in A equals to B into both 7 or something, and then see if you can work out where the mistake occurs. I'll spoil the answer now. The mistake that's made, it's at the very end, from here to here. When you divide both sides by B minus A, well, if A is equal to B, then B minus A is equal to 0. So you're trying to divide by 0 on both sides of the equation. And usually you're taught in algebra that, hey, dividing by 0 is bad, and this is exactly why. So if you allowed division by 0, you get this weird proof, like 1 is equal to 2, and you get nonsensical answers. So why am I showing you this right here? Because this is actually a really important concept in mathematics. This not being able to divide by 0. It turns out that you could divide by something like 0 if you're very careful and still make sense of the situation. And you might have seen this already if you have taken like a calculus course in high school or elsewhere, maybe in community college. So it turns out that sometimes dividing by 0 messes up things. If you do it in the right way, you could sometimes do something like this. Not exactly division by 0, but maybe division by something getting closer and closer to 0. And exactly that idea gives us calculus, and calculus allows us to solve problems in physics, chemistry, biology, and a lot of different types of sciences, and also things like economics and so on. So the applications are endless, but you want to make sure the foundation is correct, right? You don't want to divide by 0. So I just kind of wanted to introduce this idea that the division by 0 is still bad, but if you do it carefully, you could solve problems. Anyways, this concludes this worksheet video. So please finish this worksheet, and I'll see you in another video.